Good afternoon and welcome to the presentation of the study program Automation and Instrumentation Engineering. My name is Martin Novák. I'm coming from Department of Instrumentation and Control Engineering, and I will guide you through this presentation, and I will also answer your eventual questions at the end of our presentation. So first of all, let me talk about why you should study automation at the Faculty of Mechanical Engineering. You may have heard the term Industry 4.0, and the way we understand it is that this trend combines automation with industrial informatics. So it's a development of many years of research and design in the automation industry that you have been able to see in many areas, and also in industrial informatics. So it means that you are able to automate, for example, your manufacturing lines and put all those data into databases, communicate with the customer, control robots, and so on. So why you should study automation at mechanical engineering? Now you will understand the machines and processes also from other points of view than just the control theory. So you will be able to understand the construction of the machine, to understand the mechanism, to understand properties such as stiffness, elasticity. And from the automation point of view, you will be also able to work with sensors, you will be able to work with control systems, and of course with control algorithms. You will also know how to use our control system and how to apply it. So if you study automation at mechanical engineering, you will most likely not design the control system itself in an electrical point of view. So you will not design your printed circuit boards, you will not design probably the embedded software in the control system, but you will be able to use such a control system, you will be able to program it on a higher level, and you will be able to control the process or machine that you require. If you will require it, you will also be able to design your own control system from some ready-made parts. So it could be a unique control system that you require for some application, or this could be some unique measurement system. For example, if you want to some mechanical measurements or some electrical measurements, optical measurements, you will be able to design this experiment and to build such device. So the control system and control algorithm should be designed by someone who understands the system. Let me explain you how our study program works. It's a study program, so it's not a branch of mechanical engineering. It's an independent study program at Faculty of Mechanical Engineering. It is called Instrumentation and Control Engineering. It's a 2-year master program. And this program is divided into 2 specializations. The first one is called Automation and Industrial Informatics, and the second one is called Instrumentation Technology. Now, if I should describe it very briefly what it means, the automation and industrial informatics is more about control algorithms and programming, whereas the instrumentation technology is more about mechanics and construction. So in instrumentation technology, you will be building devices from mechanical point of view. You will learn how to design those devices. And in automation and industrial informatics, you will learn how to program those devices and how to work with control algorithms. Now, both programs have a common part with common subjects, and then they have a specialized part with specialized subjects. So what are the topics that you find in the common parts? Now the topics here listed are really just the topics. This is not a list of subjects because, for example, control algorithms or programming is handled with more subjects. So you will be talking about control algorithms in general. You will be working with simulations, you will be working with experiments so that you understand how those control algorithms work and also how to use them and how to tune them. Then there is a quite large topic related to programming. And basically you will be working with two groups of devices. One, let's say on the higher level of automation, is PLC, that's programmable logic controllers. Those are devices that are used for automation of industrial lines, for example. And then at a lower hardware level, you will be talking about microprocessors. So you'll see how to program some basic functions, how to control motors, how to control input and outputs. There are also classes related to sensors. So you will learn how the sensor works, how to install it properly, and how to use it in your application. Then there is a group of subjects related to artificial intelligence. So for example, you will learn about neural networks and how to use them in signal or image analysis. You will learn about expert systems that will help you to understand the machine or the problem. And there is also a large group of subjects related to machine perception and image analysis. So this relates to the fact that you very often will need a camera to analyze something in your process. You will need to analyze the image, to process the image, and then to have some algorithms that will, for example, find the desired object on this image. So those are the common topics in the study program. Apart from that, there are specialized subjects, and there are 2 specialized subjects per semester for every specialization of this. So there are 2 subjects for automation and informatics, and 2 subjects for instrumentation technology every semester. And starting from the second semester, so the summer semester in the first year, there will be also some project-based education. And I will be talking about it a little bit later. So let's take a look in more detail about the content of different specializations. So here we will see the subjects that are taught at every semester. I will start with the automation and industrial informatics. You can see that my subjects here are grouped by 2. So those are the specialized subjects just for this specialization. And they are divided by semester. So for example, in the first semester, in winter, you will learn about pneumatic and hydraulic systems. That's quite common in industrial automation, that you need compressed air and some hydraulic systems, for example, to control your robot or to control your processing plant. So that's what's covered in this subject. This is object-oriented programming, so this is about fundamentals of how to code something and how to create a program that can, for example, control your algorithm or control your robot. This in second semester you will be talking about how those devices should communicate together. So the subject industrial communication systems is about communication buses. So we'll be talking about stuff such as Modbus, you'll be talking about Ethernet and so on. Because no device today in automation is a standalone device, and every time you need some communication, you need to transfer some signals back and forth between the sensor and between your device. You need to visualize the data, you need to log the data into some database. The database will come in play as the second subject in the second semester. Here you can see database and knowledge-based systems. So this subject is about how to create a database, how to access it, how to maintain it, how to export the data from the database. So this is more software oriented, but still with respect to automation. Then in the second year, you will learn how to visualize your process. So how to create the environment where the operator can see what is happening in the industrial process. Now those systems are called SCADA systems, and this subject is about how to work with those systems, how to properly visualize your process so that the operator can easily understand what is happening in the system. Then signal processing and system identification, that's about processing some signals. So you take some signal from some sensor, for example, or from some camera, and you need to process it somehow. You need to filter out the noise. You need to look for specific frequencies. And also, this is about how to get the values for your mathematical models of the systems. So this is the part of system identification, because every time that you are creating a model of the system, you need some basic parameters. And this branch is called system identification, and that's one part that we will learn here in this subject. The two last subjects are happening in the final semester. So we will learn how to design some information systems. So this could be something with a database access, for example, something that stores data from your industrial system, something that helps the customer to get access to info that you have in the system, and also how to publish this, for example, on a website. And the last topic, optimal and predictive control systems, this is about more advanced control algorithms that are happening so far in all those specialized subjects. So we will be talking about stuff such as model predictive control and some more advanced control algorithms than standard. The second branch, instrumentation and control technology, as I was already saying, it is more related to mechanics and optics. So by looking on the subject list, you can see that it's more about how to build something, whereas the previous specialization was more about how to control something. So you can see that in the first semester you will have technical optics. That's a subject about lenses, microscopes, telescopes, and so on, how they are built, how to calculate the optical system. Then very related to that is instrument design 1 and instrument design 2. So this is about how to design the instrument so that it's precise, so that you have very small tolerances. What are the methods how to manufacture those instruments, and how to use those methods successfully to design your precision device. Then in the second semester you will have wave optics. This is related to technical optics, but it's different in the sense that here the optical system is working with waves. So it will be a description of the waves of radiation and how to design optical systems by using those methods. Then you will be talking about nanotechnology. So it's about how to produce very small devices, very small machines that might be useful for precision instruments. Very often in doing mechanical design, you will need to know something about finite element methods. Those methods are quite useful, for example, if you want to simulate the thermal distribution in your machine, if you want to simulate the stress distribution or maybe even electromagnetic distribution in some components. So this is taught in finite element method 1. So this is like an introduction to those methods and how to use them in mechanical design. Then there is a subject called design of optomechanical instruments. So this is about how to design such devices, how to design a spectrometer, for example, how to design a microscope. So again, it's a combination of optics and mechanics, but mechanics in the precision mechanics sense. So it's about precision instruments. The same is instrument design 2, so this is related to all the previous topics. So again, this is about how to design some specific, custom-made, very precise instrument. And the last subject in my list is called measurement and experiment. And as the name suggests, this will be about doing experiments with the devices, how to design your experiment, and how to evaluate the data from this experiment. Now, I also told you that starting from the second semester, we will be providing you some project classes. And we really like to do those project classes for basically 2 reasons. One reason is that if you are doing practical work in the lab, you will do something on your own. You will learn how to prepare your experiment, how to measure something, and how to evaluate the data. And also, those project classes are supposed to guide you in some specific direction. So the project classes are designed in such a way that starting from the second semester, you should start to specialize yourself into some direction. For example, someone knows that he would like to work on optomechanical devices. Someone knows that he would like to work with robots. Someone knows that he would like to work with computer software. So by selecting the project topic in the second semester, you will orient yourself in a specific direction, and then this topic will guide you to a diploma thesis that will be done in the fourth semester. So starting from the summer semester in the first year, we will have 3 project classes, project 1, 2, and 3. And together with project 3, there is the diploma thesis. So the goal of the project is to guide you into some specific domain, because it's obvious that you cannot study all domains and expect that you will understand all domains in the same way. Now, there is also one advantage of those project classes. So you can take a part in some student project or even some research project right from your second semester, and you can join some groups that are working at the department on some research or on some student project. So for you, the advantage is that you will be able to get some scholarship, because typically those projects are funded somehow, either by the university or by some industrial partner or by some research agency. So this will allow you to get scholarships. And later you can also work in this project and develop this to a diploma thesis. So not only you will be able to join some interesting topic and to get scholarship, but later you will be able to do your work and present this as a diploma thesis. Here I have few pictures of such projects that either are currently running at the department or have been running in the past. Here on the picture on the left you see an eye endoscope. That's a precision mechanical optical project related to medical research. So it's a device that can provide a doctor a picture of an eye inside, and he can then operate the eye and heal the patient. In the middle we have an example of control of electrical machine for higher speeds. And in the right we have an example of a student project that was focused in designing an active magnetic bearing. So this is just to give you a brief overview of what projects are being handled at our department. Now I have even more examples. I have selected only 3 sample projects. If you would be interested to know more about those projects, then contact the person that's written here as the contact person. If you would be interested into knowing more about other projects, then you can contact me and I can forward your message to the person that is responsible for the project. So the first sample project that I have selected is called Modeling and Control of a Complex System. And the contact person is Dr. Bušek. And this project is focused on the theoretical development of control algorithms of dynamic systems. So you can see here few examples what they are trying to develop, what algorithms and for what devices. So for example, vibration damping. You can see here a test setup, and in this test setup this coil is vibrating. It's being excited by a coil, and they are trying to develop an algorithm that will be able to dampen this vibration, which could be very useful, for example, for manufacturing machines, for mills, for lathes and so on, where you have vibrations and this deteriorates the quality of your surface as you are machining something. Now, second topic that they are doing is the control of UAVs. They are able to control, for example, a quadrotor like that, and they are working on control algorithms. For example, if they have a pendulum on this quadrotor, how to dampen the movement of this pendulum, how to transport some object if it's hanging on a rope from a quadrotor. And the third topic, and I know that they are just starting with this topic, is that they are trying to design their own walking robot. And this is an example. It's not the picture of this project, but it's an example how such robot could look like. The second project that I have chosen as an example is from the branch of precision mechanics, and the contact person is Associated Professor Hošek. And you can see here that that's the eye endoscope that I was talking about. You can see the picture here. What is the idea that this device will work? So they are working on the design of an optical system that will fit into a very thin needle like that. This needle is going into the eye during the eye surgery, and then the doctor can see the image directly on screen, and he can help the patient, he can do the surgery, and he can improve the life of the patient. Now the second sub-project is laser pumping, and that's closely related to LED coupling into fiber optics. You can see an example picture here on the top right. So for example, you can see here the LED and those green lines are how the light is being transferred into the casing, and here there is an optical fiber, how this should be coupled to the LED so that we have an efficient transfer of the signal. And the fourth sub-project is the measurement of tools for hobbing machines. You can see here an example how this tool looks like, and here you can see again some optical methods that they use to measure the profile and understand the properties of those tools. And the third sample project is related more into electrical systems. This project is currently starting, and it is about high-speed electric motors or electrical machines in general. And we are trying to develop a system that will be able to produce electrical energy and heat at the same time. And we are using high-speed electric motors. So the speed that we're talking about here is about 70 to 100,000 RPM. And we are talking about power in the range of a few kilowatts. And for this project, the contact person is Dr. Zdeněk Novák. And in this project, you can select again several topics. And those topics can range between construction, for example, of the coupling or the test bench. They can go up to the modeling, so you can create, for example, a mathematical model of the device and then design a control algorithm. And they can end up to the programming part, where you will have a signal processor or an FPGA that will control the device as a whole. And here you can see the block diagram of such system. So here is the control system. We are not building our own control systems, we are using some ready-made systems, but we are designing the software for that. Here you see the turbine and the motor, and here you can see the generator, so this will produce the electric energy. So that's what we are trying to control and design in this project. Now let me give you an example of some diploma theses that have been done in the past at our department. Now this study program that I'm just presenting is quite new. It was opened on this academic year. So far we do not have any students that have finished this study program, but in the past there was a similar program called Instrumentation and Control Engineering. So all those examples are from this older study program. The new program, the automation, was significantly updated, and we have included new topics in every branch. So what are the typical diploma theses at the department? For example, it's to design a control system for something and to implement it in an experiment. So what you see here is an example of a setup that we use in the lab that simulates a quadcopter with a suspension on as a load. So here this is like a 2D model. You can see two propellers here, left and right, and here you can see the load, and the load is hanging on some rod or on some rope. And as the plane is moving back and forth like that, this will of course act like a pendulum. And the goal here is to eliminate the movement of the pendulum so that you can very accurately position the load anywhere you like. So this is more into the control algorithm area. Then the second example is about the signal processing. You can see it's a car system for road lanes and traffic sign detection, which you see here on the second image. So this is about how to take the picture from a camera, how to process it with some algorithms, and how to find the info that you really need, so traffic lanes and traffic signs. So this is specifically going into the coding, into the software part. It's not that much related about mechanics, but it's more about signal processing. The third topic, control of active radial magnetic bearing. You can see an example here from the thesis. This was about the design of the mechanical setup and then about the electrical system and control software that was supposed to control the magnetic bearing. So to levitate some shaft in the air so that we are able to prevent the friction. The fourth example is in the area of robotics. And you can see this picture. This was a Delta robot. Delta is standing for a special configuration of the movement. And here the goal was to design this robot, to build it, and at the end the robot should sort different objects on a conveyor belt. So you can see here there is a conveyor belt, and it was picking up cylinders, picking up rectangles, and it did put them into individual boxes based on their shape. And my last example is from the domain of optics. So smart glasses, you can see here an example. And the idea here was to build a system that will be installed in your glasses that will project some image from some computer generated pictures, for example, and you will be able to directly see this info on the glasses. So in this picture you can see one of the test runs that the student has done in the lab as he was working on the thesis. Now let me tell you what you will be able to do when you graduate from this study program. What are our students typically doing? So you can work in design and programming of either assembly or manufacturing lines, or you could design or program robots. You can also work in, let's say, more software-oriented domains, such as design of control systems. So you will be designing some control algorithms, for example, for autonomous cars or control of combustion engine. Or you could work on the real pure software design, where you would be designing, for example, databases. You will be designing some industrial informatics systems that will collect info from different areas of a manufacturing plant. And you could of course work as a designer of unique instruments. So whatever someone needs to design a really unique instrument that will do whatever you need to do, then you will be able to do that. Let me talk a little bit about our labs. Maybe some labs you have been able to see in a bachelor study. Some labs are more specifically used for research or than for PhD thesis or master thesis. So we have a lab of automatic control. We have a specialized lab for programmable controllers. We have a lab for manufacturing of micro devices. You can see the picture here. We have a lab for wave optics, and we have labs for electronics and electrical machines. Now this is not a complete list, because we have about maybe 20 labs in total at our department. So this is really just a selection of what labs do we have available. Now I will be talking about labs also in a minute, and then you will be able to see and visit yourself our labs in a virtual tour. So we have prepared for you a virtual lab tour because we would like to show you our labs. The lab tour is available on this address. I know it's quite complicated, but you will have a record of this talk available, so you can get this address a little bit later. So now I will switch to my virtual lab tour, and I will show you very briefly, within a few minutes, our labs, only some of them, and I will comment on what is happening in those labs. So I will just switch to another window, and I will show you some of our labs. Now this is a virtual tour, and we currently have 360 degrees pictures from about 15 places at our department. I will comment only 4 of them in this commented virtual tour. So what you see here on the first picture, this is our lab of automatic control. So this is a lab that you may recognize if you have done the bachelor study at our faculty. And this lab is giving classes in fundamentals of automatic control. So it's about how to control some system, how to tune the controller, how to get the parameters of my system so that I can fine-tune my mathematical model. And you can see that here we have different setups. That's typical for our department. We like to build our setups like this, and then this setup is a model of some industrial system, of course simplified model. So for example, if you then select some model, let's talk about this model, for example. Now you can see that this is like a tank, very tall tank, and this specific task is the control of height of this red ball that is levitating on a water beam. So when the task runs, the pump pumps water under the ball. It levitates the ball to some distance. This distance is then measured with a sensor that's on top, and all this is in a closed loop system where it's controlled by a computer. So you can take a look on our task, on our setup, and you can also read some description of the task. For example, here you can see the ball, here you can see the sensor, and here this is the pump that is pumping the water when this task is running. And if you look around you in the lab, you can see more examples. For example, this one. This is a task where the goal is to maintain some given RPM of this rotor, which you can see here in the setup. So in this lab, what is happening is that the student is given a specific task, and typically during semester there is several tasks that are given, and he tries to control this task. He tries to understand the control algorithm, to implement it in such a way, for example in MATLAB or in Simulink, so that the task is working. If you see here this task, it's a car. Here you see an access barrier, and when the car approaches, the barrier should open. So those tasks are quite simple, but they allow you to understand the fundamentals of control systems. The second lab that I would like to show you is the lab of pneumatic controllers. Here we work with pneumatic systems and with programmable controllers. So you can see that we have different setups here. They are basically all the same, and on all of them you can build some model of a real computer control system. So for example, here you can see this is a setup with a programmable controller and with pneumatic motors. So the pneumatic motor will simulate some movement. It's driven by compressed air, and the programmable controller will control this movement based on some info that you will get from sensors, for example. It can be also controlled by a computer remotely, so that you can have the visualization of the system. So this is how the typical setup looks like. Here, this is the programmable logic controller. Those are the pneumatic motors, and all those tubes and wires, they interconnect the task to the compressed air and to electrical signals. So this is how a typical setup looks like. And the next part of this setup would of course be something on the screen, like to show some data, to show some inputs, and to show some outputs of the system. And this is the part of the SCADA systems. The third lab that I would like to talk about is the lab of electrical machines. Now, electrical machines are mostly everywhere. They are driving our cars, they're driving our toothbrush, they're driving our mixer, for example, in a kitchen. But they are used also in industrial systems. The motor is driving some conveyor belt. It's driving some robot. And for this reason, our students need to understand what are the basic properties of electrical machines. So we have such large lab where we have different setups with different kinds of electric motors. So for example, on this setup, we are able to measure the properties such as torque and speed dependence of a specific electric motor. So here you can see an electric motor that we are currently testing. This is the dynamometer that simulates the load, and we are controlling the system from a control system. We are able to change the desired speed, the set point for torque, and then we are able to load the machine and to say, okay, the torque has increased, the speed has dropped, or the speed has remained the same. And the third lab I would like to talk about is the lab of optical systems. Now in this virtual tour you will find more labs like that, so I'll just talk very briefly about what you see here on the picture. So if you look around, you can see that we have some optical systems like that. You can of course read some details about what that is. So for example, this is a device that's called a Rayleigh interferometer, and in our labs it's used in lab sessions, for example, to measure CO2 concentrations in the air. So the optical labs are typically using optical methods to measure something. For example, if I scroll to this page, now you can see an example of a typical optical bench where you see some lenses here in the middle that are currently being tested, and you can have some light source on one end of the optical bench, such as this one, and you can have some receiver at the other end, such as this one. So for example, you can measure, let's say, the resolving power of a lens. You can measure the optical power of a laser beam and stuff like that. Now there are much more labs in our virtual tour. The virtual tour is also available on our website directly, so you don't need the link from my presentation. You can just go to our website and take a look on the tour yourselves. Let me go back to my presentation, and let's give you also some info about our students. So we have 2 students that have agreed to show you and tell you about what they are doing at the department. The first student, both students are in the first year. The first student is Mr. Kengo Nagashima. So please now, Kengo, you can join us and tell us what you think about this study branch.
Yes, okay. So hello everyone. My name is Kengo and I'm from Japan. I started bachelor here from 2016 and I'm in the master of the department now. I'd like to promote the department and introduce why I chose here shortly. The first reason why I chose here is that the study field is highly demanded recently. As you already heard the introduction, there is Industry 4.0. By learning automation and instrumentation technology from a mechanical point of view, the possibility will be quite huge, since it's possible to understand entire overview, including mechanical units. And second reason is that there are supportive teachers, especially when you do some project, they will help you and answer to your silly questions. I always pay attention not asking such questions to them, but there might be less opportunities to have such moments asking to knowledgeful researcher after graduation. So you can ask them a lot and gain some knowledge and hints for your study and career. The last reason is that there are wide choices of research topics you could be interested in. As introduced already, the topics are various by its supervisor, close to mechanical, electrical, informatical, optical, control engineering, and so on. As you work on project, everything is getting connected and you might get well understandings. I think that's one of the advantages of this department. At the end, my thesis topics are design of a quadrotor as a bachelor thesis and design of a hexacopter with a RC engine, generator, and lithium polymer batteries. As you can see the picture on the right, that's the quadrotor I built. I didn't make the controlling system since they are good open software and it takes time to make and implementing. But I focused on more mechanical parts and designing to figure out why of basics of quadrotor by comparing other common and popular quadrotors. In the master, I will focus on the same way and its controlling system, like power supply, autonomous flying, and so on. I have to study a lot, such as strength testing, simulation, dynamic flow simulation, lightning designing, electrical connection, dynamic control, embedding system, and so on. It's really pricey, time consuming, and very tiring to study a wide range of fields, but it's really fun and interesting because I'm making my original one. And as I try to build something, everything I learned is connected. In the bachelor, I thought many classes were a little boring, but now I found they are very useful and helpful, since I found how to use them. Actually, I study them again quite often. The point is that in the master, you can do more practical things and you will understand what you studied in the bachelor well and find it's more fun and much more fun than bachelor. Therefore, I recommend going to a master, especially this department in mechanical engineering. That's everything from me. Thank you for your attention.
Okay, thank you, Kengo. And our second student is Miss Wongsagon Prem. So please, Prem, now tell us a little bit about your projects.
Okay. So my name is Prem. I come from Thailand. So we already heard from the experienced student is my classmate Kengo. So I will speak on behalf of students who didn't sure what to study on their master degrees. So I'm studying my master's degrees in Thailand. So my field was about like alternative energy, power plant, turbo machinery, and everything about the processes. So which mean I don't have any basic knowledges about the controlling engineering at all. And I came to Cheveute as an exchange student in my last years of bachelor degrees. And at the first time, I planned to stay here just only like 4.5 months for my exchange program, but it's end up like I have to stay at least 2 years more for my master degrees or maybe furthermore in the future. So the question is why here and why these programs? I feel like I already know about another side of the mechanical engineering, and there is one branch that I want to study, and is about the combination about the mechanics and programming, which is a controlling engineering. And the curriculum here is got my interest. There are a lot of courses which are taught in English. I should to study automation specialized field, which are about the database, programming of to control system. And there are a lot of projects which you can work on hand. Either you can assist to help professors or you can create your own project. For our programs, we have to professors say we have 3 projects and 1 thesis to work on. For example, like Kengo, right now he's working on his awesome quadrotor, and my project right now is on progressions. I'm working on autonomous car, focus on the driveless driving, avoid the obstacles, and so on. So there's a lot of opportunity in the futures if you, especially if you plan to stay here in Europe after the graduation. You can work in the industrial such as the power plant, chemical industry, or maybe like automation industry like a car, a plane, or even a rocket like SpaceX. So not just like the knowledge itself that you will get from here. You will learn how to think logically. You will learn the engineering skills because you have a lot of project that you can do. So so what is the engineering skill? So let's say like this. Why we as an engineering different from mechanician? Imagine that you have 10 days to, no, 100 days to finish the projects. As a mechanician, you will plan 10 days and on hand 90 days. They didn't think much about the circumstance of the failure that much. So when the problem just come to them, they just solve it according to the situation. While we as an engineer, we do things in a vice versa. We plan 90 days, we do simulation, test about the failure, think about the failure situation, like we change the parameters for simulate the failures, and then we on hand 10 day, easy, smooth, and flow. So in ideally, so yeah, that's all of my reason why I choose to study these programs and why I study here. So I hope that my presentation will help you guys to make the decision easier. So thank you for your attention.
Thank you, Prem, for your presentation. I would like to conclude our time with our short, let's say, motto, and that's that we give life to machines. So it's important to know mechanical engineering, but without automation, then your robot or your car or your instrument will not work at all. So thank you for your attention. I hope that we have given you an introduction what this program is about. And now it's time for questions.